Following from the previous videos, we'll be looking at representing probabilities. You could watch the previous video if you want to, but in this video I'm going to talk about tree diagrams. So all of the different facts about tree diagrams, and even tree diagrams where you have no replacements as well. So a tree diagram lists possibilities, and it's easy to use, especially if you have a few events. If you have a couple of events and if you have a few options or outcomes. The way we do tree diagram is to have your events split up into different parts, and you need to make sure that your probabilities are correct on every branch. So this is best described through an example. So I'm going to go through this example. We have a box with 5 red discs and 3 green discs. Discs. You're taking one disc at random and its color is noted before being replaced. This is important. And then the second disc is taken out. And we want the probability that both discs are the same color. You could do the whole probability on your own without a tree diagram, but let's look at the tree diagram because it's good practice. So if I take I take out the first disk. So this is my first event. So you need to split your tree diagram into different events. So this is my first event. The first disk taken out could be a red disk or a green disk. And then I'm going to take the second disk, and again, it could be a red or a green. For this example, it's simple. We only have 2 options. Sometimes you have more options. Now we list the probabilities. So we have the probability of picking red is 5 out of how many totals do I have? It's 8, and the green is 3 out of 8. And you continue putting the probabilities on the branches. So because I replaced the red, I still have 5 reds inside the box when I'm in the second disk. So I have 5 over 8, and I have 3 over 8, and the same thing here. What we usually do in tree diagrams is we complete the calculations for the probabilities because it might help us with a question. I will do that here just to show you all the different facts on probabilities, but you don't have to do it. You don't always have to complete the tree diagram. So this branch, so going red and then red, will give me the probability of getting red and then red. So notice how I'm saying I need red and red. So remember the AND rule, you always multiply the 2. So I have 5 over 8 times 5 over 8, which will give me a 25 over 64. So this is the probability of getting red and red. And this will be red and then green. So using the same logic, I'm going to get 15 over 64. This will be the probability of green and then red, which will be the same. It's not always the same, but in this case it is. And then I have the probability of green and then green, which is 9 out of 64. Now what you will notice is that if you add these up, they should give you a 1. So this or this or this or this, and you add them up and it should give you a total of 1, which is the total of probability. So this is a good way to check that your tree diagram is correct. What we want is the probability that both disks are the same color. So using the rules of probability, I want either probability of red and red or probability of green and green. And remember, or in probability translates to A plus. So green and green, and I have the probabilities already. Red and red has a probability of 25 over 64, and green has 9 out of 64, and adding them together will give me 34 out of 64, which simplifies to 17 out of 32. So that's the clearest way of using a tree diagram. Make sure you list all the probabilities, and if you want to know the probability at the end of a branch, you have to multiply the branches because you're thinking red and red, so it's an AND rule, and the probabilities should add up to 1. Now, what if there was no replacement? So same setting, but the two discs are taken at random without replacement. So I'm doing two things. I'm taking the first disc and then this first disc and then the second disc, and I'm not replacing them. So we, again, with the same probability, we want to know the probability that they're the same color. So using the same logic, so this is the first disc. I have red, I have green. Probability of red is 5/8. Probability of green is 3/8. But now we have to be a bit more careful when we're doing the other branches. So red, green, then red and green. This is my second disc. So this is my second event. And what I'm doing here is that because I've taken one red, I haven't replaced it. I have one less red to deal with. So there's 4 reds. And because I had a total of 8, but I've taken 1 out, so now I have a total of 7. So notice how the probability changes. I haven't taken green. Green hasn't changed. I've only taken the red since I'm on this branch. So my green is still 3, but my total is still 7. And you can check that these two add up to 1. And then using the same logic here, I've taken green now, which means my red hasn't changed. So I have a 4, and again, I still have 1 less total, so that's 7. But in here I've taken a green, so I have 1 less green to deal with, so that's 2, and then I have 7 left. So using the probabilities here, so I have the probability of red and red. This is probability of green and green. Sorry, red and green. This is probability of green and red. And the probability of green and green. So using the same rule as we did in the previous diagram, you multiply the branch values and you're going to get 20/56. Notice how the probabilities have changed. And the last one is 6/56. Again, check that these red values add up to a 1. Now to answer the question, we want the probability of both discs being the same color, so either red and red or green and green. So red and red is 20/56 and green is 6/56. So adding them up, we get 13/28 as in a simplified form. So notice how the probability is slightly different from the previous one. We got a 17/32 in the first one, and now it's a 13/28. So you will get a different probability when you have a no replacement. This is also called a conditional probability because what you're doing here is that I want red, given that my first choice was red. In here, you're saying that you want green, given that your first choice was red. And here you're saying that you want red, given that your first choice was green, and you have green, given your first choice is green. So something similar is this. I would like you to try out this question, at least the first part on your own. Try to do the tree diagram. Do pause the video and try it, but then I'm going to explain how to do part B. So hopefully you've noted that it's without replacement, so you need to reduce the numbers. The tree diagram is slightly different because what you're concerned about is just the B. So either you have a B or you not a B. That's all you're concerned about. You don't need to list all the letters. Another way of writing not B could be B prime, for example. So let's look at what it would look like. This is an example. This is what the tree diagram would be. So the first tile could be a B or not a B. The probability to B is 2/7, not a B is 5/7. And then picking the second tile, because I'm not replacing it, I have 1 less B tile and I have 1 less tile overall. And then my not B, well, I haven't picked any from not B, so it's still 5, but I still have 1 less to deal with, and so on. So now I need the probability that at least one of the selected tiles is a B. This at least choice gets confusing to students. At least means that if I list out all the probabilities here, so there's at least one. So either 1 or 2. So obviously because you have two tasks. So either 1 or 2 are B, which means I'm not allowed to have no B's in my list. So at least one B could be that I have B and a B. There, I have at least one B. So the least amount of B I have is 1. I could have a B and then not a B. So that's fine. I could have not a B and then a B, but then I'm not allowed to have this last branch. So what I am looking at is this branch, and this branch. What you could do is calculate the probability of each one here, calculating the probability of each branch going there. So I could have, this will be 1 over 21, this will be 5 over 21, and this will again be 5 over 21. And you could add them up because we have an or. So either this or this or this. These are all the possibilities. Another option is to actually just calculate the last one, which is a 20 over 42. And then say, well, because all of these add up to 1, I could just use that the probability of at least 1B is 1 minus the probability of no B. So this is 1 minus 20 over 42, which should give you the same answer, 11 over 21. Adding these up as well, so 1 over 21, 5 over 21, 5 over 21 will give you the same answer. So you could go the long option or you could go one less. The point of this video is to, one, use this technique, and second, to understand what at least means. Hopefully this video is clear. The next videos will go through Venn diagrams.